Let's dive right into today's explainer, where we are unpacking the massive shift from static language models to dynamic, autonomous AI agents. Look, if you've been paying even a little bit of attention to the AI space lately, you know the conversation has evolved way beyond basic chatbots. We're moving from AI that just talks to AI that actually does. But how exactly do these systems work under the hood? How do they make decisions, communicate, and actually execute these complex, multi-step workflows without us constantly holding their hands? Well, that's exactly what we're going to demystify right now.
Here's our roadmap for today. We'll start with the Agentic AI moment, move into core agent design patterns, tackle single versus multi-agent systems, look at standardizing agent connections, and finally explore Agentic RAG in practice. By following this path, we're basically going to trace a micro to macro evolution. We'll start right inside a single agent's brain and zoom all the way out to global interoperability protocols before bringing it all together.
Section 1. The Agentic AI moment. We are literally living through an Agentic AI moment right now. Think back to that initial ChatGPT breakthrough. You know, that exact moment the tech suddenly completely exceeded everyone's expectations. We're seeing a very similar phenomenon play out right now with agents. Our source material points out this absolutely fascinating example, where an AI was tasked with some online research, but during the live run, it hit a rate limit on its primary web search tool. But instead of crashing or throwing an error, the agent autonomously pivoted. It just seamlessly switched over to a Wikipedia search feature to get the job done. That spontaneous, unplanned adaptability, that is the absolute hallmark of the agentic moment we're in.
So the absolutely crucial thing to understand here is that a large language model by itself is really just the reasoning engine. It's the brain. It's brilliant, sure, but it's totally isolated. But when you embed that LLM inside an agent framework, everything changes. It gains the ability to interpret real-world information, formulate actual actionable plans, and interact with its environment to achieve specific goals. The framework basically acts as the hands and eyes, equipping that brain with memory modules, tools, and a structured way to plan.
And this brings us to a really fundamental shift in how we actually use these models. You see, most basic AI interactions operate in what we call a zero-shot mode. That's kind of like asking someone to write a complex 10-page essay in pen in one continuous attempt without ever crossing anything out. It's incredibly difficult to get a perfect result that way. An agentic workflow, on the other hand, embraces an iterative process. It plans the task, drafts a response, actively reviews it for weaknesses, and then goes back and revises it. It's a much more natural, human-like way of refining work.
Moving to Section 2, Core Agent Design Patterns. We are completely moving away from monolithic prompts and moving towards structured workflows that allow these agents to transcend simple text generation.
There are 4 foundational patterns transforming these static responders into dynamic problem solvers. First up is reflection, which allows the AI to actually critique its own work. Second is tool use, and honestly, this one is a massive game changer. It means instead of just guessing an answer based on its training data, the AI can execute real Python code to calculate compound interest or fire up a live web search for real-time product reviews. Third is planning, which is all about breaking down a huge objective into a logical step-by-step sequence. And fourth is multi-agent collaboration, where tasks get divided up among specialized AI roles, much like a human team.
Let's actually zoom in on that iterative process and see how it works using the reflection pattern specifically. Say you have a coding task. The AI generates an initial block of code, but then it acts as its own harshest critic. It evaluates the code, realizes, oh wait, there's a bug on line 5, gives itself constructive feedback, and then uses that exact feedback to revise the output autonomously. By running through this loop, the model significantly elevates the quality of its final answer. It completely changes the game for accuracy.
Which brings us to Section 3, Single versus Multi-Agent Systems. As our tasks get more and more complex, we inevitably hit the most critical architectural decision in agent design. Do we rely on one unified, incredibly smart agent, or do we orchestrate a whole team of specialized agents? It's the classic question, right? You might logically assume that a multi-agent system is just inherently superior. If one is good, a team must be great. But counterintuitively, recent research proves that this isn't always true at all. Adding more agents is definitely not a magic bullet. It's actually a really tricky structural trade-off.
Here is the real crux of the debate. A single-agent system preserves a completely coherent internal reasoning trajectory. The AI has access to the full context of the problem at all times, without ever having to summarize or translate its thoughts.
A multi-agent system, however, externalizes its reasoning into intermediate messages that get passed between different agents. This creates an unavoidable information bottleneck. Think about it. Every single time one agent has to summarize a finding to pass it to the next agent, you risk losing critical context.
And this really brilliantly illustrates the budget-aware comparison highlighted in the research. If you give both systems the exact same budget of thinking tokens, a single agent will actually often outperform a multi-agent system on complex, multi-hop reasoning. Why? Well, because the single agent spends all its compute budget actually solving the problem. The multi-agent system has to spend a massive chunk of its compute paying what we call a coordination tax, passing messages, synchronizing, and translating context back and forth between team members.
Ultimately, the science points us to a very clear architecture-task alignment principle. You should really start with a single agent baseline by default. Only escalate to multi-agent orchestration when your tasks genuinely require parallel exploration, distinct role specialization like having one explicit coder and one explicit tester, or formal verification. Basically, don't force artificial coordination onto a task that one smart agent can handle perfectly well on its own.
Okay, Section 4, standardizing agent connections. So once you've architected your agent's brain, whether that's a single genius or a specialized team, you need a standardized way to plug it into the real world. This brings us to two revolutionary protocols that are completely reshaping the ecosystem right now.
First up is the Model Context Protocol, or MCP, which is championed by Anthropic. The best way to wrap your head around MCP is to think of it as the AI equivalent of a USB-C port. In the past, if you wanted to connect an AI to 10 different tools, you had to write 10 completely distinct API integrations. It was a nightmare. MCP replaces that headache with a unified, bidirectional AI-native communication standard. One single protocol connects your AI to everything.
So what does this actually look like in the wild? Well, let's look at real-world software development. By leveraging MCP, an AI coding assistant isn't just some text generator sitting in a vacuum anymore. It becomes a deeply integrated team member. It seamlessly reads your assigned tickets from Jira, it pulls your UI layout straight from Figma, analyzes live console logs to debug errors, and then pushes intelligent commits, literally all without you having to manage a dozen separate API keys. It radically, and I mean radically, reduces the friction of context gathering.
Now, while MCP acts as the ultimate connection from the AI to external tools and data sources, there's another massive piece of the puzzle. Google recently introduced the Agent-to-Agent, or A2A protocol. A2A establishes a universal, secure mechanism for AI agents to discover and talk to each other. This is huge. It means an agent built by Salesforce can seamlessly negotiate and collaborate on long-running tasks with an agent built by Google or Atlassian. It completely breaks down those enterprise walled gardens. Let's look at a practical A2A workflow to make this concrete. Imagine an HR agent tasked by a hiring manager to find senior engineering candidates. Using A2A's capability discovery, this HR agent can securely pass subtasks to specialized remote agents. Maybe one agent built entirely by a different vendor that specifically parses resumes, and another that checks background databases. The primary agent collects all those artifacts and presents them to the human in a unified UI. It's a completely modular, interoperable agent ecosystem in action.
Finally, Section 5, Agentic RAG in practice. Let's ground all this abstract protocol and architecture theory we've been talking about by looking at how it transforms one of the most common enterprise AI capabilities today, Retrieval Augmented Generation, or RAG. If you're familiar with vanilla RAG, it's essentially like an AI reading from a static library. It takes a user query, blindly grabs some relevant text from a database, and generates an answer. Agentic RAG is an entirely different beast. It's an advanced system where agents autonomously orchestrate multi-step retrieval. To use an analogy, it's like having a smartphone equipped with specialized apps, with the AI deciding in real time exactly which app can best answer the complex question you just asked.
So, vanilla RAG relies on very limited logic and static retrieval. But agentic RAG agents, they don't just fetch text. Because they utilize those planning and reflection patterns we discussed earlier, they can autonomously decide to rephrase the user's query to get better search results. They can retrieve an initial document, realize, wait, I need more context here, and dynamically trigger an additional search. They can even cross-reference conflicting information to ensure accuracy before they ever show an answer to the user.
Utilizing that tool use pattern, a single router agent in an agentic RAG setup can seamlessly toggle between a massive arsenal of options. It might pull from a vector database for internal company policy, then jump out to a web search tool for live stock prices, use a calculator to parse some exact numerical reasoning, and then tap into software APIs to draft a personalized email based on what it found. Or, if the task is highly decomposable, a multi-agent setup could deploy separate specialized agents to do all of that simultaneously. The whole shebang.
The absolute key takeaway from all this source material is that while the capabilities are expanding at breakneck speed, discipline in design is completely critical. Multi-agent systems and unified protocols like MCP and A2A are unlocking workflows that were quite literally science fiction a year ago. But you have to remember that coordination tax. Coordination is always a scarce resource. You should build these systems starting with a coherent, single-agent baseline, adding extra agents and complex protocols only when the structure of the task explicitly demands it. We're fundamentally moving from a world where we command AI to a world where we delegate to it. As you consider this massive leap from simple conversational chatbots to autonomous, interconnected agents powered by these new universal protocols, I want you to think about something. What complex, messy workflow in your daily life or your business are you ready to finally hand over to an agentic system? Thanks for joining me on this explainer, and keep exploring the incredible potential of these technologies.